All right, so we're going to be looking at some problems from the web assigned similar to kind of what you have in homework for section 2.5. So let's look at this first one here. It says, consider independently rolling two fair dice. One is red and the other is green. Let A be the event that the red die shows 3 dots, B be the event that the green die shows 4 dots, and C be the event that the total number of dots showing on the two dice is 7. So that means like adding the dots together. Are these events pairwise independent, which means are A and B independent of each other, A and C independent of each other, and B and C independent of each other? Before we can answer that, we need to draw out kind of what we're talking about here. So if you imagine, and I'm just going to make a little chart first, and then we'll talk about our sets A, B, C. But before we can do that, we kind of need to understand what's happening. So we've got a red die and a green die. So I'm going to let the red be this column kind of here, and the green will be this one. And we have 1, 2, 3, 4, 5, and 6. And again, we have 1, 2, 3, 4, 5, and 6. Those are the number of dots on each die. And so when we put them together, what you're going to see, and I'm not going to write out every combination, but what you're going to see is you're going to have kind of looks like almost ordered pairs where you're saying this is rolling a red one and a green one. And then we'll have 1, 2, and then 1, 3, all the way up to 1, 6. We'll go down this way where it'll be 2, 1, 2, 3, all the way down to 2. Sorry, not 2. Tried to talk and write at the same time. So this third one shouldn't have been 2, 3. It should have been 3, 1. Um, yeah, because you're just changing the red one, but not the green one. So 3, 1, and then 4, 1, all the way down to 6, 1. And then you can go all the way across and you'll end up with 6, 6. Okay. So this actually is a 6 by 6 chart. So we're going to have 36 possible rolls in the entire universe. Okay. Now that's for the whole universe. That's not for our little subsets. So when we talk about this, we've got A going to be the event that the red die shows a 3. So if you think about that, just that subset, that's going to be this whole row where the red is 3. So you'd have a 3, 1, a 3, 2. You could have a 3, 3, a 3, 4, a 3, 5, and a 3, 6. Okay. B is supposed to be the event that the green die shows a 4. So that's the second position. That's the like the Y ordered pair. So that could be anywhere where we have any number up front and then a 4. So that would be 1, 4. And we would have 2, 4, 3, 4, 4, 4, 5, 4, and 6, 4. So all those are the ones where we have greens 4. And then we have anything that totals to 7. Now that's actually going to be this whole diagonal. I didn't write all this in, but in these charts, these diagonals sum to the same amounts. So it's going to be, we'd have 6, 1. And then we would have, let's see, 2, 5, or 5, 2, actually. We'll get to 2, 5 in a minute. Then we would have 4, 3. And then we would have 3, 4. And then 2, 5, and then 1, 6. Okay. All right. So that's our subsets. These are the ones where the dice add up to 7. Now we want to know if the events are pairwise independent. To prove that, we need to show the following. So we're going to have to show each of these. We need to show that probability of A intersect B is equal to the probability of A times the probability of B. We'll need to show that the probability of A intersect C is the probability of A times the probability of C. And we'll need to show the probability of B intersect C is the probability of B times the probability of C. Okay. So when we think about A intersect B, we can look and just count how many elements they have in common. So if we look at this list, it's 3, 4 is the only one they have in common. Remember, there's a total sample space of 36 different roles. So that'd be 1 out of 36. Probability of A would be how many elements are in A out of the 36. That'd be 1, 2, 3, 4, 5, 6. out of 36. And if we look at this one, we have probability of B, it's also 6 out of 36. Now we could reduce both of those fractions before multiplying them. That's 1/6 times 1/6, which equals 1 over 36. So this is true for that one. Okay, let's look at A intersect C. So if we compare what they have in common, it's 3, 4, and that's it. Yeah, that's the only one they have in common. So again, that's 1 out of 36. We already know that A's probability is 6 out of 36. C also has 6 elements. So we know we just checked that. That also multiplies out to 1 over 36. And then B intersect C. So they have, let's see, the 3, 4 in common again. And then that would be probability of B is again 6 out of 36, and there's 6 out of 36. We've already checked this. It's the same probability essentially each time. So we can say here that yes, they are pairwise independent. So that's this first choice. Now the last part of this is, are the three events mutually independent? To prove that, so this part right here was for pairwise. And we checked each of those. For mutually independent, for all three, I think Pen's not wanting to write very well. Excuse me real quick. So for mutually independent, we need to prove that the intersection of all three of them is equal to the probability of each of the three individual ones multiplied together. Now, if we can't prove that, then we can't say that it's mutually independent for all three events. So if you noticed, there was only one item that they all had in common with each other, and it ended up being that element 3, 4. So that's 1 out of 36. We had the probability of A was 6 out of 36. Probability of B was 6 out of 36. Probability of C is 6 out of 36. There were 6 elements in those subsets out of the 36 possible roles. Now, each of those is a 1/6. Now, the problem is this is not going to equal 1 over 36 because this will equal 1 over, I think it's 216. Yeah, so 6 cubed. So no, these are not mutually independent. Now, if that had been 1 over 36 equal to 1 over 36, we could say they're mutually independent. All right, let's move on to the second question. Now, for this one, we're considering randomly selecting a single individual and having that person test drive 3 different vehicles. We're going to define the events of whether they like a car as A1, A2, or A3. So A1 likes vehicle 1, A2 likes vehicle 2, A3 likes vehicle 3. Suppose that the probability that someone likes vehicle 1 is, for this individual, is 0.45. Probability that they liked vehicle 2 is 0.65. Probability that they liked vehicle 3 is 0.70. We know the union probability for A1 and A2 is 0.8. We know the intersection of A2 and A3 is 0.4. And we know the union of all three is 0.88. Now, we want to ask the question, what is the probability that the individual likes both vehicle 1 and vehicle 2? Okay, so that is the probability that we have A1 intersect with A2. That's what we're looking for. Now, we do have a formula for unions of probability. It's probability of 2 events union together. This is an OR situation. If they're not independent of each or mutually exclusive of each other, I should say, you're going to get a overlap. So this will be probability of A1 plus probability of A2 minus the intersections probability. So we're going to hope that we have all the pieces we need to plug into these other 3 parts and solve for the intersection. So we do have the union, that's 0.8. We have the probability of A1 is 0.45. We have the probability of A2 was 0.65. And imagine we're solving this as if we're solving for a variable. So we're solving for that intersection. Okay, so if we add these 2 together, that's going to be, let's see, that'd be 1.1. And then we're going to have this brought down. We'll subtract over the 1.1. That's going to be negative 0.3 equals this negative of our part we're solving for. So we're going to divide both sides by -1. So it's going to be 0.3 because our probability should not be negative, but this negative we brought down, remember, needs to be solved out. So divide by -1. Okay, so we have that one. Determine the probability that someone likes vehicle 2, given that's what this straight bar means, they like vehicle 3. So the probability of a conditional probability, when you have the given symbol, is you reduce your denominator to just the set that we were given. So that's going to be the probability of A3. And then we're looking for the condition on top that not only are they an A3, but they're also an A2. So it's an intersection probability. So we have A3, that's 0.70. We have the intersection of A2 and A3, so that's 0.40. So they've given us everything we need. And so we're going to divide that. Let me see if I can do it right here. So 0.4 divided by 0.7, rounded to 4 decimal places, I got that it's 0.5714. And you can double check that on your calculator. Okay, interpret the probability of A2 given A3. This says if a person likes vehicle 3, because that's the given condition, this is the probability that he or she will like vehicle 2 as well. So that is the first one's actually the correct interpretation. The given is always the one we know is a fact, and we're looking for the probability that the other condition is also met. Okay. All right, let's look at we're still on part C for this. Are A2 and A3 independent of events? So there's 2 ways you can check for independence. You can check for the intersection to be split into the individual multiplications. So probability of A2 times probability of A3. If that's true, we have independence. So we're questioning this. The other thing we can check is a conditional probability. And it can go either way, but if you say A2 given A3, which is the one we just calculated, what we're saying is that it should still be the probability of A2, even if we didn't have the given condition. So if this is true, you're also independent. So they're saying it doesn't really change the probability of A2 by knowing that you were already someone who liked vehicle 3. So we're going to check both of these and see what we can agree upon on this. So if you looked at the intersection of A2 and A3, did we have that given to us? Yes, that was 0.4. And then we look at our individual probabilities for A2 and A3, 0.65 and 0.70 times 0.70. And then we just need to multiply that. It's 0.65 times 0.7. That's 0.455 on this side. So notice those do not equal each other. So we can look for the one where the intersection is. It's not true, so we're looking for a no scenario. So no, the intersection of A2 and A3 did not equal the multiplication of the individual probabilities, so they're not independent. So this is one of the choices. So we already know they're not independent, but let's see what happens with this part. So A2 given A3, we just solved that, and that was 0.5714 roughly, because we did that earlier. And we're questioning, does that equal the probability of A2, which was 0.65. So no, those are not equal either. So again, we can look right here and they have it as A2 given A3 is not equal to P of A2. And notice they have this version where they have that listed up here, but they're saying it is independent. But because it failed that equation, it's not independent. That's what we're looking for. And then it says, if you learn that the individual did not like vehicle 1, what now is the probability that he or she liked at least one of the other 2 vehicles? Okay, so let's write that in symbol notation first. So they're going to like one of the other 2 vehicles, which would be either A2 or A3, given that we already know, because they already told us, we know that that person did not like vehicle 1. They did not want vehicle 1. So that's the complement of that. Okay, so if you think about that in terms of like the formula, that's going to be A2 union A3 intersected with A1 not on the top over the probability that someone did not like A1. Okay, I find it a lot easier in these scenarios to sometimes just draw out a Venn diagram and try and figure out the pieces We'll probably have to scroll back up to see, or actually I might just draw my picture up here. Just so we have it where we can see the other numbers and we have a lot of room here. So let me draw a picture. So this is going to be work for part D, just in case you're looking back at this. All right, let's draw a picture first and just determine what we were looking for in that symbol notation that I had. So I had A1, A2, A3, okay? And we've got, remember, we had the following, probability that someone liked A2 union A3, given that they did not like A1. And we said that if we wrote that in the formula notation, you'd have the union of these two intersected with A1 not on top over the probability of A1 not. So I'm just writing those formulas from down below so we can see what we're looking at. Okay, so when I think about these picture-wise, not A1, let's draw that with a highlighter. So not A1 would be anything outside of that circle A1. So everything in yellow here. Okay, everything in yellow. So that's the not A1. A2 union A3, again, we're just trying to visualize this. That's going to be A2 union A3. So if you notice, when I use the highlighter, it really does help sometimes. That little A2 didn't get put on there. Because you can see the overlapping colors here. The green is that intersection. So we need to add these three probabilities together to get that probability of the top. And then the not A1 would be all of the places where we had yellow, okay? So let's talk about what they gave us. They told us the probability of A1 union A2 union A3. I'm starting with this because it's going to help me find my outside, is 0.88. Well, the universe is the whole box, and the union of all three would be all three circles. So the yellow part that's not got the green overlap on it would be 1 minus 0.88. So if we start there, that'll tell us how much is in the outside. And that's going to be 0.12. Okay, so we have that out here. And then I need to talk about, if I call these three parts here, let's call them A, B, and C. Because if we add these three green parts and the yellow part together, that will be our probability of A1 not, that complement. That's everything that was yellow before we hit it with the blue color, okay? So that's going to be A plus B plus C plus 0.12. Well, I know what A1 is. It's 0.45. So A1 not probability is 1 minus 0.45. It has to be the opposite of that. So that's going to be 0.55. So I can replace this probability with 0.55, and I have A plus B plus C plus the 0.12. Okay, why is that helpful? Well, I can solve for ABC, the green part. The green part is my top. The yellow and green together is all of the not A1. That's all that. It's everywhere we had yellow before we added the blue. So that was also the green area. So if we can figure out what just A plus B plus C is, we'll have our numerator for this conditional probability. So I just need to subtract over that 0.12. So sometimes drawing a picture really does help clarify what you're looking for. So this is 0.43. That's my three green areas. So my probability that A2 union A3, given that they don't like the car 1, is going to be 0.43. That's all my overlapping area over all of the not A1, which was 0.55. So if we divide that, that'll give us the probability for that conditional probability. So this is 0.43 divided by 0.55. And when I did that, I got 0.7818. We'll see if they need us to go to 4 decimal places. Yeah. So 0.7848. Okay, so the picture helps with that a lot. Okay, let's look at our number 3 on 2.5. We only have 4 for this section. So this one says that we have a box in a certain supply room contains 6 40-watt light bulbs, 5 60-watt light bulbs, and 7 75-watt light bulbs. So notice in the red, those are the total numbers of each kind. So if we add that together, we'll know our total number of light bulbs. So that's going to be, let's see, 12 plus 6 more, 18 light bulbs altogether. Okay, and it says, suppose that 3 bulbs are randomly selected, and we're going to round our answers to 4 decimal places. Okay, so we're going to select 3 bulbs out of our group of 18. And depending on what kind they ask us, we might be selecting from some of our subgroups. So I could see this using our counting principles. It says, what is the probability that exactly 2 of the selected bulbs are the 75 watt? So we're picking 3 bulbs. We're saying we want 2 of them to come exactly from that set of the 75s, which has 7. So that would be 7 of those, and we're going to force ourselves to choose 2 of them. So that's, and the reason it doesn't matter, it's not a P, is because the order you select the bulbs in doesn't matter, because we can't tell the difference between one 75-watt bulb and the next 75-watt bulb. They're identical, essentially. So it's just 7, choose 2. And then we're going to pick our other bulb, because we're supposed to collect a set of 3 from either of the other 2 sets. So if you add that together, that's 11, choose 1. And then that's how many ways we can choose the 75-watt, 2 of them and 1 of the other kind. But we want probability. So probability should be a fraction. And we're saying, what if I just reach in and I get 3 bulbs and I don't care what they are? So that'd be all 18 bulbs, choose 3. So I'm going to go off to the side on my calculator and we're going to work out each of those combinations. So 7, choose 2. I work that out. So that's 7 factorial divided by 5 factorial, and then divide that by 2 factorial, or you can use the button if you have it on your calculator. So that's going to be 21 for the first number on top, times 11, choose 1 would just be 11. Anytime you choose 1, you just get the answer for the first number. And then we need to do 18, choose 3, so 18 factorial, and then you'll divide that by 18 minus 3 factorial, so that'd be 15 factorial. And then we'll take that answer and also divide that by 3 factorial using our combination formula. So that's 816. And we should be able to reuse that number because it's our denominator. But the top's going to be 21 times 11, which is 231 over 816, which is going to give me a roughly 0.28. We're supposed to go to 3 decimal places, 31. Yes, 31, because there's an 8 after the 0, so that bumps it up to a 1. Okay, now we're going to look at the next one. What is the probability that all 3 of the selected bulbs have the same rating? That means they're either all 40s, all 60 watts, or all 75 watts. So all 3 having the same rating means the same wattage. Okay, so we have an OR situation here. So we're going to have 3 separate probabilities, and OR means add them together. We don't have any inner sections here where they're going to overlap. So we don't have any subtraction for this union because they're all separate from each other. A 40 watt is not a 60 watt and vice versa. So I'm going to have all the ways to choose just all 3 are 40 watt plus all 3 are 60 watt, because that's the second option, and or means plus, or all 3 are 75 watt. That's what we're going to set up. Okay, so let's start with the first group. So we have 6 40 watts. We're going to choose all 3 of our set of 3 from them. And then that'll be 18, choose 3 still on the bottom. Plus, we could choose all 3 from the 60 watt bulbs. So that would be 5, choose 3 over 18, choose 3. Or we could choose all from the 7 75 watt bulbs. So that'd be 7, choose 3 over 18, choose 3. Now notice the denominator each time is going to be 816. So I'll just put my answers up here on the top to add together. Something to note, if you didn't have, say we only had 2 60 watt bulbs, we wouldn't have been able to select, use that for this setup that they want us to do, because you would not be able to complete your set of 3 with only those ratings. So sometimes you might have to leave a group out if there's not enough of them to fit the collection, if you're doing all of the same type. So just something to be aware of. So 6, choose 3 is 6 factorial divided by 3 factorial and then divided by 3 factorial again. So that is 20. So that first numerator is 20 plus 5 choose 3 is 5 factorial divided by 2 factorial and then divided by 3 factorial. My calculator just messed up, so hang on just a second. So 5 factorial divided by 3 factorial and then divided by 2 factorial. That comes out to 10. And then 7 choose 3. That's 7 factorial divided by 4 factorial, and then we divide that by 3 factorial. And again, you might have an easier button on your calculator for some of these if you have this N choose R button. Okay, so we need to add all those together. So that's 65 over 816. And then we'll turn that into a decimal since that's what they wanted in the directions. That is 0.0797. So 0.797. Okay. What is the probability that one bulb of each type is selected? Okay, so now we're looking at just picking, since it's a group of 3, you're going to be picking just one bulb from each group. So that's going to be 6 choose 1 times, because you're doing it in succession. When we multiply, it's because we haven't completed our group of 3. The reason we were adding between these is each of these fractions was its own way of counting a group of 3. So since we are just creating one set by choosing one from each of these, this is the multiplication principle. And we'd have 5 choose 1 times 7 choose 1, still all over our full 18 choose 3. And so this is 6 times 5 times 7, because all those choose 1s will just be the number. So that's 210 over the 816. We divide that, we get 0.2574. All right, and then the last one for this one. Suppose now that the bulbs are to be selected one by one until a 75-watt bulb is found. What is the probability that it is necessary to examine at least 6 bulbs? Okay, so at least 6 bulbs. So we're doing these one by one until we get a 75. And then we want at least 6 bulbs. So what we're saying is we're looking at the probability of 5 non-75-watt bulbs in a row. Because to get this to be at least 6 bulbs before you find one, you had to have drawn 5 in a row from the other groups. It couldn't have been from the 75. So if you think about it, this is just the probability of drawing a non-75 times a non-75, but each time we're going to keep one of the bulbs. So we're going to lose from our set. So one way we can think of this is that we have 18 total bulbs when we start, and the ones that are not 75 was 11. Since each draw is going to be just one less bulb in the pile, this would be 17. And then we would have 10, right? We're just going down by 1. And then we would have had 16, and we would have had 9. So this is 1, 2, 3 failing bulbs in a row, essentially. And then we have 15, and we would have had 8. And then the last non-75 would have came from 14 remaining bulbs. And we had only 7 of those in the list that were still non-75s. Okay. Now, if we multiply that out, that's 11 times 10 times 9 times 8 times 7, which is 55,440 over the bottom, which is 18 times 17 times 16 times 15 times 14, which is 1,028,160. Now, if you divide this, and I am going to show you an easier way to do this, but this is kind of what we're thinking. We're thinking pulling bulbs one right after the other and keeping them, and we're just doing 5 non-75s in a row. But if we divide this, I'm going to get 0.0539 when I round it. Now, I'm going to go ahead and write that over here, but there was another way I could have thought of this. I could have just said, there are 11 bulbs that are not 75, and I'm going to choose 5 of them, and then that's over the 18, choose 5 of them, because again, we're choosing 5 in a row. And then the 6th one will be that one that is not, it'll be a 75. So we have 11 factorial divided by 6 factorial, and then divided by 5 factorial. That would be 462 over, we haven't done 18, choose 5. 18 factorial divided by 13 factorial, and then divided by 5 factorial. That's 8,568. And if we divide that, we get our 0.0539 as well. Okay, so there's two ways you could have done that.